we set out at the beginning of the semester, Ben and Chris being mechanical engineering students, and Travis and I being electrical engineering students, to split our efforts and come up with a project that utilized our skills from an electrical side, from an electrical standpoint, and also from a mechanical standpoint. We set out at the beginning of the semester with many different goals, many of which we would like to discuss with you tonight. The first of which being to create a list of functional requirements that we would like to meet. And in these functional requirements, it's kind of a subset. We'll talk to you about the material selection processes that we went through, some of the mechanical considerations that we had to weigh, and also some of the electrical considerations that we had to weigh. And then we would also like to discuss, to finish things off, at some length, a discussion of the aesthetic and the cultural role that are really concerned for Dordt College, the surrounding community, and just in general. Some of our functional requirements were that we would be able to control motion of a blimp. Obviously, when you're doing any kind of remotely controlled vehicle, motion is very, very important. You're not necessarily always there, especially in the blimp type setting, to be able to reach up and grab the thing and move it around. You want to be able to control it remotely. And for that, we wanted to implement some sort of vector thrusting technique, where if you wanted to move up and then eventually move forward, instead of moving up and then stopping and then moving forward again, you could do both at the same time and kind of move backward at an angle. And that would be the type of thrusting that we were planning on doing. And the mechanical guys will discuss a little bit later how some of that was implemented with propellers and variable speed motors and that sort of thing. As a control module, we don't today have a handheld remote control. That's something that we plan and hope that a future design team, graduating engineers, would like to design for us. As an additional module to the blimp, where we would be able to not only have a handheld remote control, but also a wireless link between the ground and the blimp to be able to control it at a distance, and also something that's very portable and usable. For today, as a simulation of that remote control, we have a LabVIEW interface. We were introduced with LabVIEW with the Control Systems Project Group. And LabVIEW is a computer-based interface between electronics and the outside world. It's very graphically oriented, fairly easy to use, and easy to design this type of simulation. It's also accessible on the World Wide Web. The newest version of LabVIEW, we have our page and our control page of the blimp. We can post it on the internet. You from home will be able to go onto your computer, log onto the World Wide Web, and control the blimp from your home. And so you can see what you're doing from your home. We have a wireless video camera that's also on the blimp that will report down to the ground station, and it will be received on some sort of TV or cable network. We have something that the Dordt cable system had. We'll start off with our material selection. The first and obvious thing that we needed was a blimp bag. We're not going to make the blimp from scratch, but we're going to purchase one from somewhere. And upon some of our initial observations and some of the things we tried to figure out with pricing and sizes, and we ran into some difficulties knowing how much lift the blimp would be able to have and carry, how big it would be. And price was also a big concern. A single blimp bag like this is quite expensive. And through some searching on the internet that I had done, I came across Southern Balloon Works in Orange City, Florida, and they generously donated this blimp bag to us. So we'd like to thank them for that. It's a helium blimp. I was talking with Tom, one of their head guys down there, and he suggested that we have a model just like this. It's 13.5 feet long and about 4.5 feet in diameter. It lifts about 7 pounds, and the blimp itself weighs about 3 pounds. And so what's left over is about 4 pounds of lift that we have. And we have just about exactly 4 pounds of ordnance on the blimp to make sure it's level and neutrally buoyant, so that it would float and hover in the air, and then we can push it along with other propellers and fans, which are directed by a control system that we talked about a little bit later. And as well as the propulsion of that system with the propeller and fans and that sort of thing. An integral part of the design that I'm sure Chris and Ben would love to discuss is the gondola that you can see underneath here with the fins, or with the fans and the propellers, which also houses our batteries and our main microcontroller that Travis will talk about a little bit. And the fins in the back were also an integral part of our design that they had made for the project, and I'm sure that we would like to talk about that. But to continue with the material selection, Travis would like to talk a little bit more about the bloom bag itself and go into a little bit more depth of our control system, so I'll hand it over to Nicky.
Okay, for the most part, when people see like a balloon for a balloon or something like that, they think, it's filled with helium and the helium just kind of stays in there and it's fine. Or if you buy a balloon at a gift store or something like that, it's made of plastic called Mylar. Well, actually, our blimp here is made of just a simple, very thin plastic. It probably won't last very long. We've filled it up a couple times, and usually it lasts, about 1 to 2 weeks. It'll stay up on the ceiling and not go anywhere, but after that, it starts to lose the helium and start going to the ground, which we really don't want. So we have to fill it up again. To control this mass behemoth, as I heard somebody call it, we need some type of control system, and to control this, we decided to use a very popular microprocessor made by Motorola, namely the 68HC11. There's quite a few corporations out there that use this chip in their own products, so it would be a good choice to use as it's readily available, and there's a lot of documentation out there on how to use this particular chip. So what we decided to do is write some software on this chip that would allow us to interface with LabVIEW and control it in LabVIEW with basically serial characters over the 2 wires that we're running to the blimp right now. It communicates with serial data, and what our chip does is it takes this data and reads it and figures out, okay, this is what I need to do with this byte of data, and it takes, well, we say, okay, we want it to go up now. So we send first a byte that says this is the information for up, and the next byte says how fast we want you to go up. Then what our chip will do is look at these numbers, calculate how fast to turn on the motors, and then turn them on. Basically, for this application, it was kind of an overkill on processing power for this type of project, where we felt that being introduced previously in other classes, that was a good choice. Our main propulsion mechanisms are just a few small DC motors. You can see a few mounted here and some mounted down there. There's a few pictures there for you. Basically, they're just mounted with a couple of pieces of foam and PVC and things like that. The propellers there are what you see in the black plastic, and they're just small 3-inch propellers designed basically for moving a lot of air. And the motors that we're using are small DC, so that allows us to reverse them as well. We had thought about using motors from just like a computer fan or things like that, but we discovered that these type of fans had circuitry inside them that prevented them from running in reverse direction as a precaution for the computer, so we came up with just a straightforward DC example. Also for the gondola and the fins, we needed a lightweight, strong material that would support running into a wall or something like that without busting all the pieces, and also not weigh us down a whole lot. So we decided to go with some styrofoam and paint it over with some latex paint. We use latex because if we were to use an oil-based paint, it would kind of dissolve our styrofoam. Also, for the mounting of the fans, we wanted something rigid and stiff that wasn't terribly heavy. So we decided to go with a small diameter PVC tubing to mount the fans in, and that would also allow us to run our wires back to the controls.
Right. Now that we've heard what else was in the we get to talk a little bit about what it does. It's just a simple way about how it moves. We wanted to have 3 main directions which you can move when we started out this design project. So we thought it was fine. We needed to go up and down, and then back and forth, across. We also wanted to be able to turn. Probably the most common way to do this on a smaller blimp is just to use 1 or 2 propellers and you have them rotate into the correct direction along the course of the blimp. But we thought instead we do a more vectored thrust approach in which the propellers will be fixed and placed. As you can see, This gave us the added advantage of not only being able to rotate it, but if we had both fans turning the same way, we'd be able to drift it side to side. So it gave it greater maneuverability there. To make this happen, of course, there's a lot of mechanical considerations to go through. Probably the biggest of these is just that everything in this firm must weigh under us at 4 pounds. Originally, we thought this might be quite difficult to do. We weren't sure exactly about what size battery we were going to have. One we were looking at actually was 4 pounds itself, so that didn't give it too well. As it turned out, we got some pretty lightweight batteries fairly inexpensively. Came to a total of about 1.5 pounds, something like that. So that really helped things out, along with lightweight styrofoam we used on Gato, and a lightweight PVC pipe. This is a fairly big blimp, and yet it only lives about 4 pounds. It's because helium doesn't really lift that terribly much. 1 cubic foot of it lifts a good deal less than an ounce. So to be able to lift 4 pounds, you need about over 100 square cubic feet that is helium in there. So that kind of determined also the size of blimp we need. We could get a small 6-footer, so this is about 15 feet. That in turn kind of determines the amount of mass that we're using, which with the good old Newton's equation, of course, equals mass times acceleration, determines how much thrust we need. Through various tests, we decided we needed about at least half an ounce of thrust to get it to move at walking speed, or about half walking speed actually. So we tried to find some fans that would do approximately that. And we got a bit of a pleasant surprise here. When we actually tested the fans we found each, it was about 0.6 ounce of thrust, which gave us, with the 2 forward direction fans, about 1.2 ounces. We use that. We use a lot of code to test that. There's a lot of other considerations we need to take into consideration with our thrust testing part of this. I personally found it really hard to believe that such a small propeller like that can move such a big blimp. But the biggest thing to remember is that there's really not much mass in this whole thing. A plane which is heavier than air needs not only to produce forward thrust, but also needs to keep the plane off the ground, which is the reason it needs a lot bigger propellers and a lot more thrust. Another big consideration is drag. When we worked fluids calculations through, we found that about the maximum speed for something like this is still about half walking speed, about a mile an hour. We can vary that somewhat because the motors are variable speed. We can run them at a lower setting, but also run them actually over their rated limit of 3 volts to produce sudden burst of speed, acceleration of speed up to about 5 volts, though we try to actually at about 2.6 volts. There's also the rotational aspect that's going to take into account. Initially, we were thinking just having one propeller in the tail to move it, to turn it from side to side. But because our batteries were fairly light, we figured we could go with 2 instead. And also, our motors, which were fairly light, also didn't draw much current. So we could get by with one in the nose and one in the tail, which could allow us to drift instead of just turn into more maneuverability, as I said. And also we had to take into account drag here. Unfortunately, it really didn't matter too much at the lower speeds we were flying to.
Hello, I'm your spokesman, and my job. Not next. I could be next.
Travis and I had plenty of electrical considerations to work with. As Travis said, we were working with the Motorola 68HC11, and that chip has many, many demands on it, and there's many things that we need to consider. One of the most important things is that it needs to be maintained a constant and reliable source of power. And as Travis mentioned before, we went with the nickel metal hydride battery pack, which are not quite on the forefront of battery technology, but pretty close. They're pretty user-friendly, and we were able to construct our own battery packs, combine just a AA size rechargeable battery, but instead of the standard nickel-cadmium materials that are made of nickel metal hydride, it's more expensive, but it has a you can charge it faster, and you can discharge it faster, and it also has a higher rated capacity. And as you can imagine, some of the considerations that we needed to take in were weight versus the amount that the battery could output. Something like a car battery would put out for a very, very long time, but it's so heavy that the load that you would need to lift it would just be fill half of this room, and we needed to go with something that was in between there. And we wanted it to be rechargeable so that we could use it for a short time and then store it and then charge it again and then use it again later on. We didn't have to worry about buying new batteries for it all the time. And as Travis talked a little bit about before, selecting our microcontroller, the Motorola 68HC11 chip, it's probably a little bit overpowering for what we really need this for. This is kind of a boring task for that chip. We could do many more things that we're not having to do. There's some features on the chip that we've disabled. But as he mentioned, it's widely used in the industry. It was a very, very valuable resource for us to learn how to program the chip and to learn some of the ins and outs of how it works. And I'm very thankful that we had a chance to use that chip. Another consideration that we did have to take was the remote control aspect. Originally, we had thought of designing the remote control and transmitter circuit with this book, and then shortly after attempting to design a project like that, we realized that it probably could be another senior design project in itself. And so in our report, you'll find that we're encouraging the future Dordt College group to accept that project and design that as something they would do on their own. So we went with a lab view-based model, and we're not going to be able to fly it around for you during the presentation, but if you stick around after we're done here, we'll be able to fly it around the room a little bit, and you'll notice that there's a couple of small red wires hanging from it, and that's to simulate a wireless control model. Now I'll hand it over to Chris because this is very
Well, as with any technological artifact, we have to consider the cultural context in which it will be used. Here at Dordt College in Sioux Center, Iowa, we like to take things pretty seriously, as it should be. Our task is as students. And as Dordt College grows, it seems to find the need to build new buildings as a campus center, which is located not more than 100 yards from here. As we looked at the Dordt College Academy minutes, it said that they wanted to find something to highlight academic activity at Dordt College. As we were considering this as a possible senior design project, we looked at that and saw a correlation. So the uses in the possible uses as a in that campus center as an academic icon, which I'll discuss a little bit later, but we wanted to reflect Dordt College's goals and aspirations as that academic icon. Also as an academic tool, we've been talking about it as a possible lab use in the microcontroller use, as well as maybe physics lab uses as well to experiment with thrusting and motion. The academic icon I would like to discuss as a topic under aesthetics. We did not implement any aesthetics except for with the shape of the fins and the shape of the gondola. There's a certain sense of beauty in the way in which the electrical components work as well, but we would like to propose several things. But as we were considering that, we struggled with the concept of this being a toy. Is it a toy? But we saw this being an exploration tool as we mounted a camera on it, and we wanted to coined the term playful seriousness with this. this is somewhat playful, but it's also serious. Sometimes we forget how playful that seriousness can be as we take our task seriously here at Dordt. The design aesthetics, as I mentioned, we've implemented some, but some can be implemented in the future, possibly with this neat little fella here. Simple, but also wearing some serious armor. A word of thanks to the Dordt College Engineering Department, Drs. Dordt and Danielle, and Southern Bloom Works, as we mentioned, as well as Corridor Trading Company. Are there any questions?
Who's going to be entrusted with the blimp after you folks are gone?
Since Dordt paid for most of the blimp, was within our budget and everything, and since the blimp would have quite a bit of usefulness after we're gone for labs, microcontroller programming labs, and physics labs, and perhaps some sort of fluid flow or dynamics lab, we plan to donate our efforts and the materials that Dordt bought for us. Hang on to it, keep it in case it stays for a bit.
Roughly how long can you operate the balloon on one charge? How long do the batteries last?
The batteries that we have in there right now for the motors themselves are 3.6 volts, I believe. And on that, we can get about 2 hours to a full night to go real fast. That the battery packs that we have for the microprocessors run much longer than that, so you never have to worry about the motors themselves. But yeah, probably about 2 hours or so. And we also have a self-ready battery pack for the motors themselves, so you can extend that to 4 hours. Just by switching the battery pack.
Are you monitoring the power in any way so that you can have it sort of autonomously go back to the charging station? Suppose it's flying around in the atrium of the building needs to recharge.
One of the things that we had originally considered was you had the extra weight to spare, you could put a little metal plate in the gondola. And the microcontroller has the capability to monitor through an analog to digital converter inside there to watch the voltage on the batteries. If the batteries were to get weak, and if you were to go, it can direct itself towards an electromagnet docking station. You got it there, the magnet will turn on, and they suck the blood to it, and then charge itself. And then when it's done, release itself and continue on its like that. That's a long way.
You were talking about thrust and how it moves. Did you test it in the wind at all?
I'm not designed for that.
No, not meant for Iowa.
Indoor use only.
Well, you talked about uses in regards to the science department and like lab and that kind of stuff, but do you see it being useful to the rest of the Dordt world?
Certainly,
I know you do, that's why I'm asking.
Given the fact that we can take LabVIEW and go to the internet, one of the thoughts that we had was this could be kind of an outreach tool maybe for prospective engineering students and other students living at Dordt College. Right now you can go onto the Dordt website and take a virtual tour of campus. I guess a long-term dream with that would be that someone would implement is you could log onto that same webpage, click on the remote control page, and take a look around the campus center or the rec center and watch a track from your basketball game, something like that.
Does this thing collapse very well into a carrying case? Suppose I want to go to Western or Indian sort of pipe our program, but make that
Everything that we put on we made it detachable by using Velcro on that object. So I think, yeah, it could be as long as the carrying case was small enough. It would be.
As
except for the helium tank. You might have to go to your local ID and pick up some helium. But the bag rolls up nicely as well.
Thank you very much, John.
We line it after everybody's done here, so after the next presentation's over, if you want to stick around, we're going to try to fly around.
Thank you.